square planar complexes. This square planar complexes. So in these complexes, so generally there will be DSP2 or SP2D. Hybridization will be generally observed in this kind of the complexes. So whenever we come across about these kind of the complexes, so definitely here the central atom should provide the d orbital and one s orbital and two p orbitals. And already discussed here, if we write like this means the corresponding d orbital which is involved is inner d orbital. At the same time, if you write like this, then it means that the d orbital which is involved is outer d orbital. Based on this, we can have the inner orbital complexes or outer orbital complexes. Outer orbital complexes. For example, if I take NiCN taken 4 2 minus, which is the cyanide complex of the nickel. So in this case, the oxidation state of the nickel is +2. So as usually, if you come across the nickel, it is atomic number 28. I'm writing about the configuration of the nickel atom. So where it is having the 4s2 or otherwise 3d8, 4s2, 4p0. This is the configuration of the nickel atom. So as I told you here, nickel is present in +2 oxidation state. So in +2 oxidation state, you can see here nickel should lose 2 electrons from the valency shell, which is nothing but the s orbital, that is nothing but 4s orbital. So whenever you come across about this, so 3d8, so it will be as usual. So where the 3d orbital is having 8 electrons as usually. So you can write like this. This is a 3d8 configuration and this is nickel +2, no? So there should be no electrons in the 4s orbital of the nickel. And as usually 4p orbital is vacant. 4p orbital is vacant. Now in the presence of the Cn minus, and remember here cyanide, Cn minus is also strong p ligand. So in presence of the strong ligand, already I told you here, the unpaired electrons generally get paired up. So that's why whenever we come across in presence of the Cn minus ions, so definitely the corresponding electrons will be paired up. That's why, so in presence of Cn minus, in presence of Cn minus, the corresponding unpaired electrons will be paired up. That's why, so we can write the configuration line. So this, there occurs pairing of these 2 electrons. So this leads to give so here first orbital having 2 electrons, second also have 2 electrons, third also have 2 electrons, and fourth also have 2 electrons. Now fifth d orbital is vacant. As usually 4s orbital is vacant here and 4p is also vacant. So that's why, so this will now undergo the corresponding hybridization, that is dsp2 hybridization. And this is actually 3d orbital, this is 4s, this is 4p orbital. Now this will undergo the corresponding hybridization, that is dsp2. This will undergo dsp2 hybridization. So definitely it will be able to produce totally 4 dsp2 orbitals. So that's why, so after the formation of this complex, now every dsp2 orbital is vacant now. So the Cn minus is able to donate electron pair to this particular dsp2 atomic orbitals. Now this leads to form the corresponding complex, which is a tetrahedral complex. Tetrahedral complex. The same we can show like this. So here so all the 4 dsp2 orbitals. So this is 3d orbital showing only 4. So all these are paired completely, and dsp2 1 2 3 4 only. So all these will have 4. Now each Cn minus. So Cn minus is donating one electron pair to this corresponding dsp2 orbital. So we can electron pair donated by the Cn minus. Here also we can see here. Just and also Cn minus, another Cn minus. So this is one Cn minus, third one, and fourth one. So everyone is able to produce one this. So automatically, so we'll get the corresponding complex, and we are saying here the hybridization is dsp2. So it will be the square planar complex. Square planar complex. So apart from this, we can also take various examples, and this is one of the suitable example to understand the concept of the formation of the square planar complexes according to the valence band theory. Now let us see how the corresponding octahedral complexes will be formed. Octahedral complexes where the coordination number is 6 or number of ligands surrounded by the central metal atom is 6. So let us see here in the octahedral complexes in the formation. Octahedral complexes. There, the hybridization of the central atom or the ion will be sp3d2 or d2sp3. Either sp3d2 or d2sp3. Again here also, if it is generally outer orbital complex, and this will be inner orbital complex. So you can see here. Okay. Now if I take for example as FeCN taken 6 4 minus. So where the oxidation number of iron is in +2. So here this is the corresponding complex. Again here also we have Cn minus. Again it is a strong field ligand. So that's why if you see here in this formation of particular complex here. So iron in the atomic state, iron atomic number is 26. So where they have 3d6 configuration, 4s2 and 4p0. 4p0. Now here I'm sure we are aware that the iron is in +2 oxidation state. So definitely the electron must be lost from the outer orbital, which is 4s atomic orbital. So in +2 state, iron will have the configuration of 3d6 as usually. So 3d orbitals should have the 6 electrons. So 1, 2, 3, 4 like this. 3d6 and 4s0. This particular 4s have 0 electrons. 4p also 0 electrons. This is we can see in the case of Fe2 plus. Fe2 plus. Now this is basically undergoes sp3d2 hybridization or d2sp3 hybridization. Just you have to check it. So here Cn minus is a strong field ligand. As I told you here, in presence of this, the corresponding electrons have the ability to undergo pairing. So because of this reason, here we have 1, 2, 3, 4. 4 unpaired electrons are there. So in presence of the Cn minus, these unpaired electrons get paired up. That's why, so in presence of Cn minus, as I already told you, this is a strong field ligand or strong ligand. So the unpaired electrons will be get paired up. So because of this reason, so this here, these two get paired up, these two get also paired up. So finally we can see here 3D will have this kind of arrangement. So 1, 2, 3. So these three get completely paired up. That's why, so 2 electrons here, 2 electrons here, 2 electrons here, all these are paired up. And usually 4s is vacant and 4p is also vacant as shown above. Now, in order to facilitate this D2sp3 hybridization, so we can see here we have 2 d orbitals and 1 s orbital and corresponding p orbitals. So that's why now this will undergo the corresponding hybridization as usually, so which leads to give the totally D2sp3 6 atomic orbitals or 6 hybrid orbitals. 6 hybrid orbitals. So 6 atomic orbitals involved in hybridization to give 6 hybrid orbitals of D2sp3. So now, so once we got these corresponding hybrid orbitals, now every Cn minus will donate the 1 electron pair to the corresponding D2sp3 orbitals. So we can see the same thing like this. So this is 3D. So these 3 are completely paired with electrons, and here we have 1, 2, 3, 4, 5, 6. So these will form nothing but the corresponding sp3 D2 orbitals. So every Cn minus, as discussed in the previous case, now this is able to give 1 electron pair to this. So we can see here 1 electron pair which is donated by the Cn minus. We can also see another Cn minus is also able to donate electron pair. This is a second coordinate covalent bond, and the next one also will provide us the third one. So then fourth one and the fifth one and the sixth one. This is how we can form the, or we can get the corresponding complexes. So every Cn is able to give the electron pair. Now we can see here how the bond is formed. Now if you see here particular complex here, FeCN taken 6, 4 minus. So in this case, and if you see here all the electrons we see paired up completely. That's why, so this particular complex is considered as the diamagnetic. There is no unpaired electrons at all. And also here this is D2sp3 hybridization. So that's why it is, we can call it as inner orbital complex. And as all electrons are correspondingly paired here in presence of the Cn minus, so we can see, we can also call them as the low spin complexes. Low spin complexes or inner orbital complexes, spin paired complexes. This, see, we can have this. So around this is the central atom iron. So you can see here the arrangement of the corresponding ligand. So this is able to give 1 electron pair Cn, another electron pair. This is also Cn group. This is another electron pair given by Cn or Cn minus. This is an electron given by Cn or the Cn minus, and another electron Cn, and here also we can see 1 Cn. So above this we can see that what is the charge we can see here, 4 minus. This is how we can see the formation of the, how the corresponding tetrahedral to square planar, then followed by the octahedral complexes. Now let us take another example which will have the sp3 D2 hybridization. Yeah. So you can take another example of iron complex where iron H2O is 3 plus, taken 6. So the oxidation number of iron is plus 3 here. Water is a neutral ligand. And remember, water is a weak ligand or weak field ligand. So in presence of this, you can see the corresponding electrons which are present in the iron central atom, they won't undergo any pairing. So let us see how exactly. So we can see this here. So iron is 26 in atomic state. It have again 3d6, 4s2 and 4p0. And it is in plus 3 state, no? So definitely it has to lose 3 electrons, 2 from s orbital and 1 from the d orbital. So that's why iron in plus 3 at ionic state, so have 3d5, because after losing 1 electron should have 3d5. The same we can represent like this. So 1, 2, 3, 4, 5. And 4 is have lost both electrons. Now this is vacant, and coming to 4p, it is having vacant, and coming to the 4d is also vacant here. As I told you here, water is a weak field ligand or weak ligand. So in presence of this, there is no pairing of these electrons will take place. That's why, so these do not participate in the hybridization. That's why, so 4d orbitals involved in hybridization in the case of this formation of the particular complex. So we can see here, this is the orbitals which involve in hybridization. This is sp3d2.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.